This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 1, Pressure Vessels, Thin Wall and Thick Wall. A vessel holds pressure two ways. If the wall is thin, the stress is a uniform membrane, and the hoop stress is twice the longitudinal. If the wall is thick, the stress varies through it, largest at the bore. That's what the Lamé table gives you. We'll set the thin wall gate, size a welded wall to code, then read the thick wall table. Concept 1. The thin wall membrane. When the diameter to thickness ratio is greater than 10, treat the wall as a thin membrane. Hoop stress is pressure times diameter over 2 times thickness. Longitudinal is pressure times diameter over 4 times thickness. So the hoop is twice the longitudinal and governs. That's why cylinders split along a lengthwise seam. Concept 2. The sphere. A sphere has no unique axis, so hoop and longitudinal are equal. Pressure times radius over 2t. That's half the hoop stress of a cylinder at the same radius, which is why a sphere is the efficient shape for containing pressure. The Handbook also writes the thin cylinder in radius form. It's the same result, since the diameter is twice the radius. Concept 3. Sizing a welded wall. The code thickness is internal pressure times inside radius over the allowable stress times the joint efficiency, minus a small pressure correction. The joint efficiency derates the welded seam. It multiplies the allowable stress, never the pressure. A lower efficiency means a thicker wall. Concept 4. The thick wall. Below the gate, the membrane assumption fails. The stress varies through the wall. The Lamé table gives every cell. The key fact: the tangential stress is largest at the bore, the inside surface, and it uses radii, not diameter. That inner surface maximum is why thick vessels crack from the inside out. Setup. A cylindrical vessel runs at 1000 psi. First a thin case, 20-inch bore, half-inch wall with a code allowable and a joint efficiency. Then a thick contrast, a 4-inch inside radius and a 6-inch outer radius. The plan: check the gate, get the thin wall stresses, size the wall, then read the Lamé bore stress. Solve. Part 1. Diameter over thickness is 40, well above 10, so the membrane model holds. Hoop stress comes out 20,000, longitudinal 10,000, exactly the 2-to-1 ratio, and the hoop governs. Solve. Part 2. That 20,000 hoop already exceeds the 15,000 allowable, so the half-inch wall is under-designed. The code thickness works out to about 0.8 of an inch. The joint efficiency pulled the allowable down before the pressure correction. Size to that, not the as-built wall. Solve. Part 3. For the heavy cylinder, the ratio is 4, below the gate, so switch to Lamé. Tangential stress at the bore is 2600. Dropping to 1600 at the outer surface. The bore is the hot spot. Force the thin wall formula here, and you get one flat number that misses the gradient entirely. Traps. 5 ways this bites. 1. The gate picks the model. Thin wall on a thick vessel misses the bore. 2. Thin wall uses diameter. Lamé uses radii. Don't mix them. 3. Hoop is twice longitudinal, and a sphere halves it. 4. Tangential stress peaks at the inner surface, not the outer. 5. Joint efficiency multiplies the allowable stress, not the pressure. Quick recall. Thin wall above the gate. Hoop is pressure diameter over 2t, longitudinal over 4t, sphere over 2t on the radius. Code thickness carries the joint efficiency. Below the gate, the Lamé table. Tangential greatest at the bore. Golden rule: check the diameter to thickness gate first. It decides everything that follows. Next up, Lesson 2, Piping and Fluid Power. The same thin wall vessel becomes a pipe rated by Barlow, and a hydraulic cylinder is a pressure vessel that does work. Its extend and retract forces come straight from bore and rod areas. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.